Quantum computers have the potential to be the most important, the most dangerous, and the most unpredictable invention of our lifetime. They can even become all three of those things all at the same time. We hear this term come up every now and again. It sounds very futuristic and speculative, but quantum computers are very real. They exist right now, and they are on the verge of becoming a big part of our daily lives. You don't need to be a physicist to understand the role that these quantum machines could play in changing the world as we know it, and I'm here to guide you into the quantum realm. Let's go. Okay, Marvel's Ant-Man has some questionable physics at best, but one thing that Professor Pym does have right is that the smaller things get, the stranger the laws of physics that govern them will become. This is important to keep in mind as we go along. You've probably seen a quantum computer before. It looks pretty weird, more like some kind of a cross between a golden chandelier and a giant squid than anything we traditionally associate with a computer. But that's largely because our current viewpoint is a little too narrow. This thing is also a computer, the first computer actually, as in the first ever. It was found at the bottom of the Mediterranean Sea and dates back to ancient Greece. It is known as the Antikythera mechanism. It was used to predict the movements of the sun, the moon, and the earth. It could have forecasted a solar eclipse decades in advance, the same as we can today. And this computer also looks pretty weird, although these shiny golden mechanisms you're seeing are just artistic recreations. The real artifact is actually a bunch of fragments encrusted with thousands of years' worth of ocean gunk. Calculating machines have taken many forms over the centuries that they've been used by humankind. So, in many ways, the quantum computer is just the next phase of evolution. But in many other ways it's not that at all. Modern computers as we know them are defined by bits. A bit is the smallest unit of data that a computer can process and store. Bits are the building blocks of every piece of digital information you have ever experienced. A bit always exists in one of two states, kind of like a switch. This is why we say that computers speak a binary language. The state of each bit is typically represented by either a 1 or a 0, but it can also be represented by on or off, up or down, left or right, as long as each bit is holding one of two potential values. This is binary computing. The physical manifestation of a bit is called a transistor. This is like an electronic switch, and again, it can exist in one of two potential states, on and off. So, the more physical transistors you have, the more bits of information you can process at one time, which is an oversimplification but it gets the point across. We've been constantly trying to make these transistors smaller and smaller over time so that we can fit more transistors into increasingly smaller devices. This old desktop calculator from the 1960s used 250 transistors. A current model iPhone has 19 billion transistors in its main processor chip alone. To accomplish this, we have reduced the size of the transistor down to a width of just 3 nanometers. This is too small for the mind to truly comprehend. It's only slightly wider than a strand of human DNA, which is 2.5 nanometers. It's possible that transistors could be reduced to the size of 1 nanometer by the end of this decade. There is a physical limitation on how small they can be. But regardless of how small you make a transistor, it is still limited by the binary nature of the bit. It can only ever be in one of two states. And this is where quantum computers come into play. A quantum computer uses its own unit of data measurement, which is the qubit. And these things can get pretty weird. Qubits also represent ones and zeros just like traditional bits, but qubits can also represent both 1 and 0 at the same time. They are non-binary, and this potentially gives qubits the ability to hold vastly more information than traditional bits. The physical manifestation of a qubit is achieved by manipulating the spin state of subatomic particles, either protons or electrons, causing them to spin up and down or left and right, creating two distinct states, your 1 and 0. Except quantum mechanics allows these subatomic particles to exist in multiple states simultaneously, so they can potentially be spinning in all directions all at once. Remember, the smaller things get, the stranger the laws that govern them. Here's what that looks like. If you put two bits together, we know that each bit will represent either a 1 or a 0. So, regardless of the combination, you have 2 bits of information. But when you put 2 qubits together, you end up with the equivalent of 4 bits of information. This is because there are now 4 possible combinations of 1 and 0, as each qubit has the potential to be both values at the same time. If this is starting to sound familiar, then that's probably because you're already a quantum physicist, or you've heard about a thought experiment called Schrödinger's cat. The basic explanation of Schrödinger's idea is that you could take a cat and put it in a box, then put something else in the box that could potentially kill the cat, like a cup of poison, then you seal the box. Now, as long as there is no way for us on the outside to know what's happened inside the box, then we have no evidence to suggest that the cat is dead or alive. Maybe it drank the poison. Maybe it didn't. My cat eats plastic but refuses to eat chicken. They're unpredictable creatures. As long as we have no observable method to predict the fate of the cat, then it may be considered simultaneously both dead and alive at the same time. This is referred to in quantum physics as a superposition, and it is a state in which qubits are able to reside. They are two potential outcomes occurring simultaneously. Now, the trick here is that the moment you open the box and check on the well-being of the cat, that superposition collapses back into a binary. The cat will either be dead or alive. And the same applies to qubits. They eventually have to pick a side and resolve as either a 1 or a 0. But that time spent in a superposition allows the quantum computer to explore a vast network of potential combinations before arriving at a final answer. This superposition is where the quantum computer gets its power. When you start adding up all of the potential values from the superpositions of multiple qubits working together, then you start to get some pretty staggering numbers.